The SN1 reaction mechanism for nucleophilic substitution is distinctly different from SN2. Take a look. We've got some carbon with the leaving group attached and three other things. We'll write their stereochemistry just to remind us. And rather than say what these are, we'll just say 1, 2, 3. There are two steps in this mechanism, and the first one simply involves bond breaking. That leaving group leaves, and when it does, it leaves a carbocation, carbon with a positive charge. It has three things attached to it, not four, so it's not tetrahedral, it's planar. And of course the leaving group is around. In a second step, this carbocation reacts with the nucleophile. That's easy to understand. At the moment, I'm going to write a negatively charged nucleophile, but it doesn't have to be, and often in the SN1 reaction, this is a neutral molecule. The key requirement to be a nucleophile is to have a pair of electrons to form a bond with carbon, and there they are. And so they're available to share a bond with carbon. And notice something interesting. That nucleophile can add to the carbon on the same side that the leaving group left, or that nucleophile could approach from the other side. So in a sense, there are two different products made. They may be different or they may be not. Depends on what 1, 2, and 3 are. But to be careful, we better write both products. Here's the product that the SN2 reaction forms. You'll recall we call this inversion of configuration. And the product that's formed if the nucleophile adds to the same side as the leaving group. Now there's one more very important thing to notice about this reaction, and without drawing an energy diagram at this point, it would be easy to guess, and would be absolutely right, that this bond breaking step requires energy and is relatively slow compared to the bond making step. This second step is relatively fast. This is called the slow step, this first step. In kinetics terms, it's called the rate determining step. And when we talk about kinetics and what order the reaction is, it's this slow step that we need to focus on. It's the slow step that is the bottleneck, and so it's the slow step that kinetics measurements measure the rate. And so we'll notice that in this slow step, there's only one participant that affects the kinetics. So let's write down the key characteristics of the SN1 reaction like we did for the SN2 reaction. It's a two-step mechanism. It has first-order kinetics. The rate is dependent on the concentration of substrate, but not nucleophile. The nucleophile is not involved in the slow step, and you can add a lot of nucleophile or less nucleophile. It can be a better nucleophile or worse nucleophile. It doesn't affect the rate. The relative rates for substrates with different numbers of alkyl groups attached is just the opposite that we saw for SN2. Tertiary is faster than secondary, which is much, much faster than primary. Primary just doesn't happen. We'll just put methyl there too. Methyl doesn't happen. Better leaving group, faster reaction. Better nucleophile, no effect on the rate. And the stereochemical outcome? We'll take a look. This takes place by making essentially a 50-50 mixture of the two enantiomers in a case like this, and we call that racemization. So in the SN2 reaction, we had complete inversion of configuration, and with the SN1 reaction, we have just the opposite. We have equal amounts of the two possible stereochemistries. So as you would guess, because the intermediate is formed in the rate determining step, its structure determines its stability. So its structure has a very large effect on the relative rates of the SN1 reaction. This structure of the carbocation then is something we'll need to look at carefully. What makes some carbocations more stable than others is essentially the question. And the more stable the carbocation, the more readily it's made. So it stands to reason that the reaction goes faster. That last statement I made brings to mind the Hammond Postulate, which we'll have to talk in terms of when we really want to understand the relative rates of the SN1 reaction.